Hello there, people. It's Miss Adams from Flamingo Math. We're going to finish up lesson 3.9 today, talking about inverse trig functions. So if we have an invertible function for sine, cosine, and tangent, that means we've restricted the domains. We talked about this in the last lesson for each of those functions. And we can apply the property of inverse functions. If f of f inverse of x equals the identity x, and f inverse of the f of x equals the identity of x, we can apply these properties to sine, cosine, and tangent and their inverse functions to the following properties. So I'm not going to read through each one of them, but sine of sine inverse of x will give us the identity if every x is between -1 and 1. But if we want the sine inverse of the sine of x to equal x, then we have to restrict that domain to -π/2 and +π/2 inclusively. And these truths hold true all the way through for sine inverse, cosine inverse, and tangent inverse. So just be aware of these properties as we walk through these examples. Let's find the exact value, if possible, for the sine inverse of the sine of 2π/3. So here's what I want to pay attention to right here. The sine inverse of sine 2π/3 will give us a value if we're inside the interval from -π/2 to +π/2. Now, let me point out something interesting here. Let's say we think about the unit circle, and we are restricted from +π/2 to -π/2 for sine inverse. So we can only look at our answers in here. And here's our problem. My angle is over here, 2π/3. So we know 2π/3 is not in our restricted interval. So the first thing we can do is think about working inside this problem. And we know that the sine of 2π/3, so let's find that value first. The sine of 2π/3 is, sine is the y value, so we go out a half and go up square root of 3/2. Sine of 2π/3 is that value. Sine is square root of 3/2. So now, working from the inside out, we want the sine inverse of radical 3/2. And this is just an angle, right? We're looking for the angle where the sine is radical 3/2. And where does that happen? That happens when theta is π/3. Okay, so π/3, over here on our unit circle, π/3 has a y value of radical 3/2. Now, how about the next one? Cosine of cosine inverse 3π/4. So on the cosine, think about cosine. Cosine is going to be restricted from 0 to pi. So we can only look in this area. And we're looking for what happens. Cosine of cosine inverse. Cosine of cosine inverse. We have to be between -1 and +1. So this expression is not defined because x is square root of 3/4. X is 3π/4. So our theta, if you want to call it theta, is 3π/4. That's not on our interval from -1 to 1. That means cosine inverse 3π/4 is not defined. So this one is not possible. And then part C, we want cosine inverse of cosine 7 pi over 6. This one's just like the A example. We want to find the cosine of 7 pi over 6. We want to do that first. What's the cosine of 7 pi over 6? Cosine of 7 pi over 6 lives in quadrant 3, and that value is negative square root of 3 over 2. That's the x coordinate here. Negative radical 3 over 2, negative 1/2. Cosine is x, and sine is y. And then we can substitute that, find the angle. So cosine inverse of negative radical 3 over 2. Now we're back to our restricted area. Because we're restricted here, we can only look between 0 and pi. So on this interval, at what angle will we find negative radical 3 over 2? That's going to be in quadrant 2. It's going to be right here, quadrant 2, at 5 pi over 6. So these, you just have to be careful, think about them, understand the restrictions and the notation. Moving on, in example 9, we're going to practice this same concept with some graphing. So we want to find the exact value for the cosine of the sine inverse of negative 1/2. To me, that seems like we could go look inside of here. This is an angle here. The sine inverse negative 1/2 is an angle. It's saying, for what angle will we find negative 1/2? That's going to be down here. You can think of this as a triangle now. So sine is the opposite side divided by the hypotenuse. This is side opposite. This is the side that's the hypotenuse, using that relationship. And then we want to find the missing side. So the missing side is going to be the hypotenuse squared minus the leg squared. 4 minus 1 is going to be the square root of 3. That's our missing side. Let's think this through now. As we move on x, the x coordinate is positive and the y coordinate is negative, and the hypotenuse is never negative, and this is our angle of interest. So we've taken care of everything inside of here, and we've got a sketch to match it, and now we can answer the question, what is the cosine of our angle? Because this piece is our angle, right? The cosine of the angle is the side adjacent divided by the hypotenuse. So the cosine of the sine inverse of negative 1/2 is the adjacent side, that's radical 3, divided by the hypotenuse. So radical 3 over 2 is the answer to our question. You want to try number 10 on your own, or you want to work through it with me? I'm looking at the inside piece, just like number 9. I want the cosine of the angle, that's 5 over 13. So cosine is the side adjacent divided by the hypotenuse. The adjacent side divided by the hypotenuse. So the adjacent side is 5. Here's my angle of interest. Hypotenuse is 13. And we're looking for the missing side. So we can find that missing side by calculating the hypotenuse squared minus the leg squared. That's 144. Square root of 144 is 12. So we have this side is 12. We know this is a right triangle, and we're looking for the sine of the angle, right? The sine of the missing angle is the side opposite length divided by the length of the hypotenuse. So the opposite over hypotenuse is our answer to that composite trig expression. Example 11, if 0 is less than x, and that's less than 1, we want to write the sine of the cosine inverse of x as an algebraic expression in x. So what does that mean? That means we want the sine of cosine inverse of x to be the sine of an angle. And what do we know about that angle? Because this piece here is the angle, right? The inverse is an angle. So the angle is, that's sine is the opposite over the hypotenuse. And they gave us this little information. X has to be between 0 and 1. So what if we said the side opposite, we could say sine of theta is opposite over hypotenuse. So we could say sine is x over hypotenuse. How would we find that missing leg here? We want to find the length of this missing leg. So we could do that using the Pythagorean theorem, and the sine of theta is going to be a squared plus b squared is c squared. So we have the hypotenuse squared minus x squared is the length of this side. So this side is the square root of 1 minus x squared. So what's the sine of our angle? Sine of the cosine inverse is the sine of our angle, and that happens to be radical 1 minus x squared. It's that length on the other side. The sine that's opposite divided by hypotenuse would be this expression here. Ooh, that one hurts your head, doesn't it? Example 12, it's a little practical application. An airplane flies at an altitude of 5 miles toward a point that's directly over your house. We want to write theta as a function of x, so that shouldn't be too hard. Theta would be, what do we have? We have the opposite and we have the adjacent, so that sounds like tangent to me. So tangent inverse of the opposite over the adjacent would be our angle, and we want to find the angle when the x value is 8. So when this is 8, we're trying to figure out theta is tan inverse of 5 over 8. So what we're going to do on our calculator is either enter that in the calculator. Theta is 0.5586 of a radian. Now, if you wanted to know a degree, just because we're familiar with degrees, we could convert that 0.5586 radian by multiplying by 180 and dividing by pi, and we'd get something around 32 degrees. But remember, we don't do degrees in AP Pre-Calc. That was just for a better understanding of how big that degree is. Okay, you think you got this? See you on the next video for lesson 310.